Smartness intensified. Alright. Science is part of our culture more today than ever before. You can stream self-landing rocket missions on YouTube, and advanced scientific topics like black holes, quantum computing, and epidemiology have made their way into the headlines. But if you want to build the insight needed to make predictions and build new things, a thousand years of scientific principles stand in your way. The puzzles in this course will start to bridge that gap. But all of them I need to go through. I've got 5 of all of them. Welcome to your first lesson. Lessons typically take around 50 minutes to complete. You won't need any extra materials to work on this lesson. We've all had one of those satisfying aha moments while poring over a crossword puzzle, deducting the right arrangement of Sudoku numbers, or finding the key piece at the crux of a jigsaw puzzle. Aha! Puzzles are fun because they present a challenge for your brain. They all have a simple structure and clear set of rules solving them. But in this course, you won't be solving puzzles involving general knowledge, numerical patterns, or image reconstruction. We'll be tackling puzzles in the natural world. To solve a puzzle, you need to know its rules, and when the puzzle is nature, its rules are scientific principles. The physical sciences are the study of these rules, whether it is in the form of chemistry, biology, or physics. I'm 11, by the way. I'm learning this by myself. Throughout this course, we'll unwrap the basic building blocks of the natural world, helping you understand motion, forces, energy, heat, light, and time. Everything follows these rules. The world is beautifully connected by the laws of physics that you will find in this course. There's no better way to see the power of scientific principles than to use them. To kick things off, we're going to think about a peculiar problem. For reasons left unspecified, a bouncy ball sits on a stand as a commuter train barrels towards it. After the train collides with the ball, how fast will the ball be moving? Probably 200 kilometers an hour. To get started, let's think about how balls bounce. Bouncy balls are nice because they're Bouncy balls are nice because their motion is simple. It can be described with the following rule. When a bouncy ball collides with a much heavier object at rest, it bounces off at the same speed in the opposite direction. If you don't have a bouncy ball lying around, you can test this out by dragging the ball around and dropping it. What the hell am I supposed to do that? Ball. Pokemon cards, stacked upon stacks of Pokemon cards. Does that work? Oh no, I left my highlighter open. Oh, because the lid's gone. Oh, yeah. A ball. A ball would be nowhere. Right, I don't have a ball. Oh, could I do it? So. Yeah. Should be going at the same speed, yeah. So if you throw the bouncy ball at a wall with a speed of 2 miles a second, what will its speed immediately will its speed be immediately after it bounces? 2 mile 2 miles a second. Correct. 88% of people got that right. Yo. Because it going off in the other direction. I think so. It would go. That would. I'm correct. It would go 200 kilometers an hour once it got hit by the train. First rule might not seem to get us any closer to think about the train. After all, the train's moving, not the ball. But that's because we're looking at things from a particular perspective. The one where the train is moving, this leads the one where the train is moving. This leads us to our second important rule. Nature doesn't spend the nature doesn't depend on how we look at it. A physical process is the same no matter what perspective we use to think about it. Whenever we think of it as a 200 kilometer an hour train per hour train that collides with a ball at rest, or a ball moving at 200 kilometers an hour that collides with a train at rest, the ball and the train will end up with the same relative speed. Okay, next thing here. Sometimes all you need is a little change in perspective to turn a hard problem into an easier problem that you know how to solve. See if you can do that here. A train is barreling down the tracks at 200 kilometers an hour towards a bouncy ball that sits on a stand. After the ball and the train collide, how fast will the ball be moving? You'll have to use the two rules together. What? It only did one rule. What was the other rule? What? Wait, no, what was the other rule? What was the other rule? Rule: nature doesn't depend on how we look at it. A physical process is the same no matter what perspective we use to think about it. Okay. There are a few ways to look at this situation. The first way is to look at it from the perspective of someone standing on the side of a train tracks. To this person, the bouncy ball is sitting at a rest on a tee when it gets hit by the train moving at 200 kilometers an hour. The second is the perspective of someone standing on the train. To this person, the ball moves at 200 kilometers an hour toward the train, which is motionless. If we try to solve this problem in the point of view of the bystander, the proper approach is to write down the total energy of the system and the total momentum before and after the collision. This would produce a set of equations that we could solve for the final velocity. But that would be wasted effort and take us beyond the scope of this course. The problem is much simpler in the perspective of the train passenger. In the train's point of view, the ball approaches at 200 kilometers an hour, and the ball bounces back the other way at the same speed, 200 kilometers an hour. This is just like a ball would hit a wall at speed u. Wait, u ultra. Okay, I'll give ultra. And bounce off with the same speed in the opposite direction. Why? What? Perspective of a bystander. So, from the train's point of view, the ball recedes at 200 kilometers an hour, but the train itself is moving at that speed. So, the true speed of the ball, from the point of view of the Earth, is the sum of these two speeds, 400 kilometers an hour. This technique is switching perspective or reference frames is a powerful tool for thinking about the world. Bing, bang, bing, 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 bing. Oh, the train shoulder is over here, not down there. So the velocity would make the ball go underneath it because it would trample it downwards. But in reality, if a 200 kilometer per hour ball was hitting a train, it would smash right through it. As it turns out, this problem is much simpler than we think about it from the perspective of the train. For the person on the train, the ball approaches the stationary train at 200 kilometers an hour. Since the train is much heavier than the ball, the first rule tells us that the ball will bounce back at the same speed it approached 200 kilometers an hour. However, the second rule tells us that the outcome is the same no matter how we look at the collision. In the case, the outcome is the relative velocity of the train and the bouncy ball. Since the train is moving at 200 kilometers an hour, we need to add its velocity back in to find the final speed of the ball according to a bystander on the side of the tracks. So the ball bounces away at 200 kilometers an hour plus speed of the train to the bystander, 200 kilometers an hour, equals 400 kilometers an hour of the speed of the ball to the bystander. What? What? Okay. The thinking involved in solving puzzles is a unique blend of following rules with imaginative association. Only by combining both can you see a pattern or a twist that the puzzle conceals. If all goes well, you're able to use that hidden insight to form new information and ideas. The process will be exactly the same with physics. We'll bring the rules, you bring the imagination. Yeah. Thank you for your feedback. 5% is done of nature is a puzzle. No, I've done nature of the puzzle. Earth thing, Earth stuff is 5% done. Wait, let me see. What's happening with?
Dr. Freeman? Ah, their voices are so compressed because of the era. Yeah. When is your birthday? The 14th of August. When is your birthday? 2000. I'm not telling you. When I don't trust you. Birthday? I don't trust you. I do not trust those animated their gestures warm and welcoming.
Wait. Window capture. Window capture.
His reward is the canoe. This time he can sit in the canoe.
Properties.
That's actually really
No,
funny.
not properties.
I really like
I need
that
to
one.
do it.
I really like that.
performance mode. No.
No, I do. No, this is what you don't understand, Rin. This is what you don't understand, okay? I do have to come.
No, not gonna get me, not gonna get me, not gonna get me, not gonna get me.
That was really well cut. That was well.
No. Oh no.
Gordon!
Oh God. Gordon!
You distracted me
Look out!
with Gordon saying that.
Yeah, thank God. If I had to think about that more, I would have. Oh my God.
You cannot use the double golf cup for the fucking Slurpee. This right here. This is Slurpee cup.
Okay.
You use this time. Every time you use it. I was made for it. What's wrong? Look like Ray Whiskey Frank.
This one is the Slurpee cup. They're on 3 lives now. So now.
Okay. That was impressive, actually.
Mr. Bean dance. Ba-da-ba-da-ba-da-bum. You slumber a cucumber.
Oh yeah, that's what it was from.
My normal amount of dumbness.
Maybe we'll get one of those today, Jack. You try it.
I am not the same person as Dream.
That was I am not. I can't believe that.
I am not Dream. I am not Dream.
Dum. Ba-da-ba-da-ba-da-bum. Ba-da-ba-da-ba-da-bum. Ba-da-ba-da-ba-da-bum.
Oh no, it doesn't. That's so funny. I like that. We don't really have time for that.
Yeah, no, it's so funny because you just like press the order button, you just hear that, and it gets me every time because I never expected.
It's not, but thank you. Happy birthday, man. It's your birthday.
Thank you.
I thought it was really funny that we're showing a dinosaur for birth because we're all dead.
But then again, that's what aging means. That got really morbid. Wow. The text is okay.
No idea.
The alphabet. I mean, I know some.
I understand, but I also like. I mean, I knew you would.
I wonder what he's gonna say.
Come. He's done it. Come.
Wow. So if they rehash the jokes, we rehash the jokes. We're just gonna go for it.
We will give you the same reaction if you donate the same thing. Okay.
That's not.
I don't know what he's saying. Wow. Wow, that is
The most gamer man on earth.
Wow.
That man.
Yes.
I don't remember him saying that.
Yes.
And the Lord said. I mean, it does work, in fairness.
Oh my God, that makes sense.
It does make sense.
It does make sense. Now for my normal dose of smartness. Intense smartness. Intense smartness. Why is people talking on Jeesh? Baga 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 bang 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 baga 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 bang. Science rules. How some nature follows certain rules. Learn how to use them. Okay, fine. Apply rules. So let me look at honey. And today 400 gold. So nah. Alright, science rules, science think, big brain. So our first stopping is mechanical gearings. A lot of good science gets done without any sophisticated principles. Sometimes all you need are intrinsic relationships, like how two objects touch or what kind of shapes they have. The puzzle is one of those cases, and you can probably solve it with your intuition. The gear has 10 teeth, and the big gear has 50 teeth. When the small gear rolls around the big gear, how many times will the arrow return to its intentional orientation, pointing upwards? 1, 2, 3, 4, 5, 6, 7. Let me do that again. 1, 2, 3, 4, 5, 6, 7. Let me do it. 1, 2, 3, 4, 5, 6, 7. Fine, 6 then. Yes! 1, 2, 3, 4, 5, 6. Here, X Games Mall. So, woo. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Continue. Baga 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 ba baga 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 ba baga 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 ba. The next stop on our tour is heat transfer. Prepare to meet your first rule. All objects release heat in all directions. Emperor penguins living in Antarctica form large huddles with up to thousands of penguins to stay warm. Penguins on the outside are very cold, but they consistently shuffle so that each penguin spends a tiny fraction of their time on the outer edge. Penguins on inside are surrounded by other penguins giving off heat, which they absorb, keeping them warm. When a penguin is on the outer edge, will they feel any warmer than if they were standing alone? Please, please, I think so. Getting stumped is part of learning. Yeah. You've probably heard of Newton's laws, which explain the motion of most ordinary objects. One of Newton's great instincts, known in any other circumstance as Newton's third law, is our next rule. For every push, there is an equal push in the opposite direction. If you push a box to the right, you will receive an equal and opposite push from the box to the left. See if you can figure out this next puzzle. The fire the fire hydrant below receives water from the ground at high speeds and redirects it toward the right. At some point, the rusty bolts that hold it into the ground are going to break. And the hydrant comes free. In what direction does the hydrant? Up and to the left. Yes! Let's go! Let's go! Let's go! Let's go! Let's go! B-R-C-D-D. Can read this one. Ouch. Alright, our last rule on the tour concerns the way that light moves. Rule: light takes the path between 2 points that takes the least time. Typically, this means the light travels in a straight line, as a straight line is the shortest distance between 2 points. However, this can change when the speed of light isn't consistent. For example, light travels faster through air than through water. You've lost a ball at the bottom of a pond and shine your flashlight into the pond and to try and find where it sank. Which path will the light take to reach the ball? B. Show explanation. What is it? What? Yeah. You're literally looking at B. Oh, because this is faster through. Oh. Look, so if you don't understand like me that I just did, this isn't the correct part. Because if you look here, the light that goes through there goes quick and then goes slow for a bit. Here goes quick for a while and then goes slow for a little bit. So A would have been the correct answer, because on air it moves faster, so it would be able to get there quicker, and then it wouldn't spend as much time going down here than it would in here. I think. Yeah, I'm correct. Now you should have a better idea of the approach we're taking learning by doing. In this tour, we kicked the tires on a few rules. If you missed some problems, don't worry about it. In the course, we'll spend more time with each idea, getting our bearings with some lighter puzzles, so that we can love you too, Mom. So we can step up to truly perplexing. There we go. But don't take our word for it. See for yourself in the light chapter. You can I know I'm doing this. Can explore more laws that govern electricity and magnetism, and how they illuminate our world. The next quiz offers a preview into these rules, and you can start unraveling these concepts in a house of mirror. Oh, 9%. Science rules. Learn how light moves by solving these mirror puzzles. Let's do I think for whether to keep streaming and do this last one, or end streaming and then do this one for the next big brain time. So, eeny, meeny, miny, mo, touch the baby on the toe. If it screams, let it go. Eeny, meeny, I am not going to flip it. Eeny, meeny, miny, mo, touch the baby on the toe. If it screams, let it go. Eeny, meeny, miny, you. Oh, right, continue. House of Mirrors. When you see yourself in the mirror, that the light bouncing off of you is reflecting back to your eyes. This is pretty straightforward, but things start to get more interesting when light is reflected more than once. If you've ever put two mirrors in the same room, you know that when the angle is just right, you can peer into an infinite abyss. In this exploration, we'll use puzzles to unpack some fascinating optical effects. Before we figure out optical puzzles with more than one mirror, we need to be clear about what happens to light to us at a single mirror. I know how to do this one. When a beam is reflected, the angle the incoming light makes with the mirror will always be equal to the angle that reflected. So if it get reflected from here, it would go back like this. So like bam, 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 bam. So if someone shone right down, it'll just shine right back up to them. Someone shone like this, it would duplicate back off this. But if someone shone like this on the table, there was a mirror here, it'd shine onto this, and shine all over here. Then if there was a mirror here, the thing that shine would shine here, here, to here, and then pass back here. So then you could do something like put stuff like here. Yeah, put a mirror there, and then so you shine like that, bounce off there, 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 bounce off there. So it just keep going forever. Yeah. Chugga 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 down, chugga 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 down, chugga 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 down. Right, continue. So light beams leave the gem in all directions, but only the beams that lead in some direction are seen by the eye. Use the locator near the gem below to see where the beams leaving in different directions end up. Where on the mirror can light beams reflect to enter the eye? Not B and not C. It has to be A. There has to be a perfect V. So someone hands you an open box with a hole on one side and activates you and invites you to look inside. Little do you know, the person who built the box laid a mirror on one of the walls. The rest of the walls don't reflect light. How many jewels can you see when your eye is in the center of the hole? Needs to be bam, bam, there, there. It's you. Yeah. So, a different box has the same layout, but it now has two mirrored walls. How many jewels can you see in this one? If you look there, you'd see it. Let me see. Remember, Elliot. So a mirror like this and a mirror like that. You'd look into here, you'd see that. So you think you'd see either two or more than three. If you look through here, it can bounce off. So you'd see it here, here, and here. It's moved, so yeah. Eeny, meeny, miny, mo, touch your baby on the toe. If it screams, let it go. Eeny, meeny, miny, you. Wait, what was it? Wait, what was it? 2. Oh, because there's two mirrors around them. Yeah, because you could see from there, and can see from there, you could see two different particles or two different places to go. Oh, so if you don't understand, you can see from, because you could they could reflect from here to here, so that's the easiest way. And there's another way, because it could reflect from this mirror and then reflect from this mirror into here. Yeah, this is your eye. Yeah. No. Wait. With two mirrors, it is possible to see light from a single object, the jewel, coming from two different directions. In the same box with two mirrors, do the images of the jewel appear to be the same distance from you? Wait 1 second, guys. Pardon? So, the reflection of an object in a mirror is called an image. It doesn't matter where you look at the mirror from, the image of the gems appear to stay in the same place. You can see it yourself. See it yourself by moving the eye below to different positions. Reveal the ray and image by tapping the button below the diagram. The second rule of this quiz tells you precisely how to find the location of the image. Dream. Bugga. Saucy bugger. You saucy bugger. Ooh, you saucy bugger. You saucy bugger. Saucy bugger. You saucy bugger. Image. So you'd see the image reflected like that. Flip. So look there. You see two. Or you see. What? Oh, the same. Okay. So now you've finished. Now you're handed a third box. This one also has two mirrors, but is laid out a little differently. Where is the image for the ray that makes one reflection on the left mirror and then enters the eye? See. A. Now you've handed a third box. This one also has two mirrors, but it's laid out a little different. Where is the image for the ray that makes one reflection on the left mirror and then enters that?
See? You sussy bugger. You sussy bugger.
To find the image, you can project out the ray that reaches your eye. The tortoise is Oh, you sussy backer. Oh, what I did, I just aimed at the sea and it goes right at it. But hey, got it. Perfect.
You sussy baka. 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 You sussy. You sussy baka. You sussy baka. I can only do that more. Yo. So, my reflection. That. So, rays of light from the gem reflected of the mirrored walls can produce two images of the gem on either side of the real one. Because the two mirrored walls face each other, rays from the jewel can reflect off either mirror before exiting the box. When you look into the sides of the box, how many gems do you see? What? One? No. It needs to be 1, 2, 3, 4. Boom, boom, boom. Boom, 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 boom. Hey, let's go. So, let's see. 3, 4, 5. 5, 5. Yes.
So, circle, circle. This is bad. Circle, 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 circle. Oh. Oh. I can't do all the fun stuff. Alright. Sadie Backer. Sadie Backer. Well, this is the end of knowledge time. And now we'll only go on to episode 2 of knowledge time. If I have to pay a lot of money.
per year.